Good afternoon, everyone. We're going to listen to Robert on about the large FHIR service databases. The presentation will take 15 minutes, and afterwards there will be 5 minutes to ask your questions, so please reserve your questions towards the end. That's it. Robert, the floor is yours.
Awesome. Thank you. Welcome, everybody. I'm Robert Johnson. I am a senior software engineer at Microsoft. I work on the Azure FHIR service, both the Azure API for FHIR and the Azure Health Data Services FHIR service. And today I'm going to talk about strategies we've used as our services have scaled up and we've had to store more and more data as our customers keep getting larger. So, quick overview. First, I want to talk about a common alternative that we considered when we were looking into how to solve this problem. And then I'm going to talk about 4 strategies that we've implemented to help us shove more data into the same database. Couple clarifications first. There are 3 sizes that I am going to talk about. There's going to be the overall database size. This one's pretty self-explanatory. There's going to be the search parameter index size. So this is how much space is taken up by all of the search parameters that we need to use to enable FHIR searches. And then there's the raw resource size, which is the actual space taken up by all of the just raw FHIR resources stored in the database. Second thing, FHIR has a wide variety of use cases. The numbers that I will share here are averages. Your mileage may vary. And also, there are always going to be trade-offs that you can make to increase the amount of size that a database can store. If you wanted to, you could throw all of your FHIR data into a storage blob, but you would have a hard time running search over a storage blob. So all of the strategies that we did were with the mind to preserve performance. So increase size, keep performance the same, or in the best case, improve it. So the first strategy that we looked at was sharding our data. So using multiple databases to store the FHIR data. The obvious advantage of this, you can scale infinitely, in theory. If you can get enough databases to put all the data in. Unfortunately, there's a lot of cons to this. The first being that in order to do this, you need to create slices of data that will preserve the functionality that you need for your workflow. So say that you are running patient searches. You need all of your patients in one slice because trying to run a search over multiple different databases and then coalescing the results is a bit of a nightmare and can greatly increase service latency because you're either running it sequentially, which has obvious latency implications, or you're running it in parallel and then getting back a bunch more data than you might be wanting and then needing to pick which pieces you actually want to return. So this can require creating a proxy in front of your FHIR service in order to properly route calls. You also run into the issue of having to pay for all of these multiple databases. These things aren't cheap. And when you're trying to run a sorted search, if your data is coming from multiple databases, you need to sort it on the server side while still maintaining pagination, which can be a tricky operation to achieve. So what did we actually do? So one of the first things that we did was we set up our FHIR service so that whenever a customer sends in a resource, we will check to make sure that this resource is different in some way from what we have stored in our database. So If the two results are identical, so same everything except for the submission time, obviously, we will just return a 200 to the customer and not change anything. This will never even hit the database. So the last update time stays as the last time that it was actually updated, not the last time it was attempted to be updated. Pro, this reduces a lot of clutter in the database and it makes put requests idempotent, which can be important for some customers. A con is that there's no record kept of this attempt. Usually we have found that this isn't a problem, but in theory it could be. Whereas the size savings is highly dependent on use case. We implemented this when we had one particular user that was sending a lot of duplicates because every time that they were updating a patient, they were resending all of their insurance information, even though the insurance information hadn't changed. And those resources were very large. So this shrunk down their daily growth significantly. Another strategy we did was we started compressing raw resources in the database. So when we actually have the raw FHIR resources in our database, we don't need them to be human readable. In fact, that's a bit of a detriment in our mind. We don't want it to be easy to read our customers' data. So we compress them and then just store the compressed version. This does require a bit of extra processing time, both on save and load to do the compression and decompression, but we've noticed that the extra time is irrelevant in the just general range of time that a search takes. And we've noticed that it reduces the size of the resource by about 66%. So this was a pretty significant space savings for us. Another strategy that we've done is allow users to control how history is recorded. By default, our FHIR service has full history, so you could go back as many versions as you want, all the way to the beginning of the FHIR service. But for some users, this isn't necessary. They will never look at historical resources. This is usually the case if the FHIR service is not their source of truth. It's just used for some other purpose. In this case, we allow them to turn off history on a resource type by resource type level. So if you don't want it for, say, observations, but you do still want it for patients, you can do that. This removes the need to store historical versions, obviously saving database size there. Cons, you can no longer look at history, but this is why we don't enable it by default. So space savings, once again, this one was very hard to measure and it's very dependent on the service age and the user behavior. If a customer is just sending new resources constantly and not really updating anything, it doesn't save much at all. But for some customers who are constantly making meaningful updates to resources, this can save a lot of space. And as I said, if this is just a secondary service, they don't need the history to begin with because it's being stored somewhere else. So this is a little bit of a rehash from the happy presentation this morning, if anybody saw that. I'll admit I was a little disappointed to be the second presentation on large FHIR services, but oh well. So another thing that we allow our users to do is control which search parameters they have enabled and are being stored in their database. So this allows customers to go through all of the, I believe it's 1,375 that we support by default just from the FHIR spec, and turn off any that they don't need. So pros, obviously this is saving a lot of indexing space. And it also saves processing time when creating or updating a resource. But you can't use a search parameter that's not indexed. So we generally recommend that customers evaluate what their use case is, what are their workflows, what search parameters they need before they start using this feature. So in terms of space savings, when we looked at a lot of our databases, we found that on average, the search parameters are taking up about 2/3 of the total size of the database. Now, this was after we had done the resource compression, but we found that any space we could save here was going to be very valuable. The savings obviously are dependent on the customer's workflow. If they have a very targeted workflow, they can save a lot of space by turning off search parameters. If they have a very general workflow or they have an unpredictable workflow, they might not be able to turn off many at all. But for the ones that could turn off a lot, we saw savings of upwards of 60% of the search parameter index size. So I will say once again, results may vary a lot. And for 2 of these, the rejecting duplicates and history control, we don't have reliable numbers at all. But for the others, we managed to reduce our size by about 2.5 times, or we fit 2.5 times more data into the same database. And we've also noticed a severe drop in the growth rate of the services. Once again, this is harder to quantify, unfortunately, because it depends so much on user behavior. So that's what I've got. You can reach me here if you want to. And are there any questions?
So is it at least 2 of the approaches mentioned seems like they might have adverse effect on analytics use cases. Okay. Have you guys seen that in practice? And if so, how do you mitigate some of the read-heavy uses for analytics?
Which ones are you talking about?
So for example, the first one was around the compression,
Yep.
the compression strategy. That one requires on load to decompress to be able to view the data, which means if you have heavy loads on read through analytics, that you're going to incur latencies every single call there. That was one. The other one, which is around the indices,
Yep.
the one where you reduce the number of indices being tracked. That means if you're indexing on one of the items in the analytics queries, that index is going to cause you to have high latency for those queries involved.
So for the compression, the measurements we saw, we have not seen a notable increase in latency. We're talking maybe 1 millisecond on a 20 to 30 millisecond call. It wasn't relevant, even on heavy reads. As for the search parameters, I don't fully, I don't understand what the question would be.
So on certain parameters, if you're running analytics,
Yeah.
and some of those required in the analytics, the fields you're looking up,
Yeah.
if they're not indexed,
Oh, okay.
if they're not indexed,
So,
and the basically querying of those, it's going to cause that to increase the latency for that query.
So actually, it wouldn't increase the latency because the call wouldn't succeed. We don't allow searching on unindexed search parameters. So that would be where a user would just need to look at what their use case was, and if they're going to run analytics that need search parameters, certain search parameters, they need to keep those search parameters enabled.
Yeah, a great talk. A similar question. On the compression, I mean, like what type of algorithms are you using? Are you compressing it in sort of the FHIR format, or are you moving it to a different format? Because I'm wondering if you're going to do some type of large language model, you know, just processing of vast amounts of data, you know, how that would work out with whatever compression algorithms you're using.
So the compression algorithm we're using is just a generic text compression. We're just taking the raw JSON and turning it into binary format. It would not be usable for a large language model in the form that it's in our database. We do not intend for anything to have direct database access. If an LLM or any other analytics needs access to the data, they have to do it through the API. So the form that it's in the database wouldn't affect that. Ideally, you would export the data first and then run it on the exported data.
Does that answer your question? Okay.
Just in terms of the sharding, if you only do data extraction, which is something that we focus on, do you see any issues if you do patient-by-patient data extraction? You don't need to essentially link the patients as you extract them, and you don't need to do any sorting. Do you see any other, do you see that charging could be a problem in that context? Because, so from our perspective, it probably shouldn't be, but then you said there are some contexts, and so my question is that, do you believe that that would be one context where it could be a problem?
So I think that there are sharding strategies that could work. And what you're describing, we would need to talk more about it to know if it would. Because we are a generic FHIR server, we don't have a great, we need to make it so our customers can shape our service the way they need, and offering, we could not find a way to let the customer define a sharding strategy that we could use on their behalf.
Yeah, and so like you said, where sharding is a problem, is one of the examples is sorting. Do you have some other examples where it actually breaks? Because I mean, if you're on one patient, it doesn't seem, as long as you're within one patient compartment and your shard is done by a patient.
Yep.
I just can't see any, as long as you don't query across patients or want to do anything like that. But
I would agree that that would work. I would say that that's a very narrow work case. I can't speak for every user, but I know a lot of our users have cross-patient queries and cross-resource type queries that that would just not work for.
Okay, thank you.
Any other questions? No? Well, thank you, Robert, and thank you, everyone, for your questions.
Thank you.